This is an introduction lecture to the mole, and I think the easiest way to think of the mole is simply like a dozen. So just like you don't want to go to the store and buy one egg at a time and count them individually, a dozen seems to be a really convenient unit for the amount of eggs we might use in a week or something. And so same as the mole. Okay, it turns out the atoms and molecules are so tiny that you need a lot of them in order to be able to even see it with your naked eye or work with it. In fact, you need about this many atoms or molecules in order to just have a small pinch in your hand, typically. So a mole is just a convenient unit for this teeny tiny little entity, atoms and molecules. Again, the mole is equal to 6.02 times 10 to the 23 of anything. Now, nobody's going to want that many marbles or tires or eggs, okay? It only is used by chemists, and it's huge. It's a huge number, and that reflects how teeny tiny molecules and atoms are, all right? To give you an idea of how tiny atoms and molecules are, if you had this many marbles, if you had a mole of marbles, that would be enough to cover the entire Earth and extend up into space a ways. So it gives you an idea how small molecules and atoms are. But mole is a counting number, just like dozen is a counting number. You can count how many of something theoretically in a mole. The original definition came from how many carbon atoms there are in 12 grams of carbon. All right, so you'll see as we go along, you literally can't count atoms, okay? So we have indirect ways of counting them. But that was the original definition of where moles came from, is somebody said, okay, we're going to get exactly 12 grams of carbon. Now, you probably remember that the molar mass of carbon is also 12, right? And so they said, okay, we're going to call that a mole, and we're going to see how many atoms are in that much. So from now on, you will hear when you talk about moles, again, it's a counting number. It tells us how much, okay? So if you have a mole of water molecules, you have this many water molecules. If you have a mole of NaCl formula units, you may remember ionic compounds are referred to as formula units and not molecules, you have this many formula units. Now, in this chapter, we are going to use the mole as a conversion factor. As you might imagine, if you're a chemist and you're doing reactions, you're going to mass out quantities. You can't count atoms or molecules. You're going to mass out 1 gram, 5 grams, 10 grams of something, but you need to be able to know how many molecules that is or how many formula units that is, right? Because there's going to be some chemical reaction going on. You need to know how many of each. So we need a conversion factor that takes us from a mole to particles, and you'll see later in this PowerPoint also from moles to grams, to mass. So if you remember back to when we did introduced dimensional analysis, any type of conversion factor that takes us from one unit to another, in this case from moles to particles, or the other way, we arrange our equality is a ratio. And depending on what units we're starting with and what units we want to end up with, that equality can be expressed as a ratio, right side up or upside down. Okay, so we'll go through it just to remind you of how to do that. So for example, let's say a problem gave you a certain number of particles. It said, okay, I'm starting with 10,000 molecules of water, okay? And it may ask you, how many moles of water is that? Well, you would use this conversion to get from the number of particles, in this case we were talking about molecules, to the number of moles. And you can go the other way too. So to make this conversion seem as easy as it actually really is, let's say somebody asked you to go to the store and buy 5 dozen eggs. And then they said, well, how many eggs is that? You do that conversion in your head without even realizing what you were doing, would be my guess. So, but to show you kind of in slow motion what that conversion looks like, because that's what we'll have to be doing with mole calculations. So if you have 5 dozen and you want to know how many individual eggs that is, what you're doing is you would use the conversion factor. You know that in 1 dozen eggs, there are 12 individual eggs, right? And so all you're doing when you do that mental math is you're multiplying 5 times 12. So what that means is there are 60 individual eggs in 5 dozen eggs. And so that's the same process we're going to be using for moles to molecules, moles to grams, etc. So quick reminder, when you're doing dimensional analysis, whatever the units are of your beginning given information, in this case dozen, you want to make sure when you line up your conversion factor that the units in the denominator of your conversion factor match the units of your starting information. And so algebraically, we can now cancel out those units that we don't want anymore and then just carry out the math. So let's just switch dozen to moles, okay? So I have 5 moles of atoms. We'll say carbon atoms, okay? And I want to know how many atoms, individual atoms, that is. Well, you'd use a conversion factor. So you would have mole down here, and then you would use what you know 1 mole is equal to as far as atoms. It's equal to 6.02 times 10 to the 23rd individual atoms. And then, of course, the units of your given information should cancel with whatever units are in the denominator of your conversion factor. And then you just do the math. It'd be 5 times 6.022 times 10 to the 23rd. It's an easy example, but as long as you follow that process each time, it should remain easy. Let's go the other way around. Let's say, well, no, this is the same way. Number 2 is the other way around. So if we start with 2 moles of lithium and ask you how many atoms, again, you're always going to start with the given information, 2 moles of lithium. Then whatever units are in your given information must be the exact same units you have in the denominator of your conversion factor. And so 1 mole of anything is equal to 6.02 times 23rd atoms. So then you just do the math. 2 times 6.02 times 10 to the 23rd. Now let's go in the other direction. Let's say that I gave you the number of atoms of something I had. So that's now your given information. Now be careful, because since atoms are your given information units, that means that the units in the denominator of your conversion factor must match that so that they cancel. So now we need to have atoms in the bottom, and we're trying to get to moles. The units you're trying to get to go in the numerator. So now be a little bit careful doing the math, because what the math is in this point, 6.02 times 10 to the 23rd divided by, see, this is in the denominator, divided by 6.02 times 10 to the 23rd, okay? So this many atoms is 1 mole. That conversion between moles and, we'll call it particles, okay? So we're a particle, anything that you can count, so that would be atoms, molecules, formula units, any individual things that you can count, okay? So to get from moles to particles, or back the other way, we're going to use Avogadro's number as a conversion factor, 6.02 times 10 to the 23rd particle in a mole. All right, so right now I want to talk about another common conversion, which is going from moles to grams, or mass, whatever the mass is. And this is going to be a particularly useful conversion Because what do chemists do to measure out, practically speaking, to measure out the amount of something? They weigh it out on a balance, right? And so we need some way of converting whatever we weigh out in the balance to how many moles. So then we can look back at the chemical reaction and figure out how many moles of the other reactants we need. So we need a conversion factor between mass and moles. We need a conversion factor between mass and moles. That conversion factor is called molar mass, which you may have encountered in high school chemistry, hopefully. The molar mass of a particular element is found in the periodic table. So, of course, in the periodic table, every element has its own square, and then below that square is the average molar mass of all the isotopes, right? That is what we're going to use as a conversion factor if we're talking about carbon, all right? So, one carbon atom has a molar mass of 12, that's atomic mass units, all right? This is weird, so pay attention to this. Instead of having only one carbon atom, one single atom, if I had 1 mole of carbon atoms, so that is 6.02 times 10 to the 23rd carbon atoms. If I had that many carbon atoms, I would have 12 grams. So this is on purpose, y'all. Whatever the mass is on the periodic table, that number, 12.0 for carbon, is the mass of one single carbon atom, one single whatever the element is, in units of AMU. Or if you have a mole of those atoms, it's that same value but with different units, so grams. So that's really handy. So the amount of mass, the amount of grams in 1 mole is what we call molar mass. Okay? The amount of grams in 1 mole of anything is called molar mass. I made that pretty sloppy. Sorry about that. All right, so now before we start doing dimensional analysis and calculations, it's going to be important to find the molar mass of compounds, not just elements and atoms. And so, for example, let's look at calcium phosphate because it has a lot of different atoms in it, right? We have 3 calcium, and we have 2 phosphorus, and we have 2 times 4, 8 oxygen. And so to find the molar mass of calcium phosphate, you're literally going to just add the individual masses of each atom that's in that formula. So 3 calcium atoms, look at the periodic table, the mass for calcium, 40.078, and do the same for all of the atoms that are in a compound, and then add them together. So we would say the molar mass of calcium phosphate is 310.18 grams per mole. Now the actual molar mass, notice its units, grams per mole. That's how many grams are in 1 mole of calcium phosphate. This is what we're going to use as a conversion factor. Let's look at a really simple example. Let's say that somebody told me we have 3 moles of aluminum metal, just the atom aluminum. How many grams is that? Well, what is the process we go through? Make yourself go through this process. This is how you show your work. It's how you catch errors. So the given information, which is what you always start with, 3 moles of aluminum. Then for dimensional analysis, that means that the denominator of our conversion factor must have the same units as this given, so the denominator needs to be moles of aluminum. Now, I'm going to say something really important here. Anytime you are doing a conversion that involves moles, I want you to get into the habit of putting a number 1 in front of moles. Now, what goes in the numerator is the unit you are trying to get to. What did the problem ask us? They asked us for grams. So grams of aluminum goes in the top. So now you just have to remember that anytime you're converting between grams and moles, as we are here, that the number you're looking for that has units of grams is the molar mass in the periodic table. So now we're just going to look at the periodic table. We are going to find the molar mass of aluminum, and that is going to go right here. All right, so if you look in the periodic table, the molar mass of aluminum is 27 grams. Another way, this is the equality that becomes our conversion factor, which is 1 mole of aluminum equals 27 grams, or you could flip it upside down. Same thing, 27 grams of aluminum is 1 mole. And you'll decide which one of these ratios to use depending on the units that you start with. In this case, we started with moles, so we want to make sure we use this format that has moles in the bottom. And then we just do the math. 3 times 27 divided by 1. And we get the answer that there are 81 grams of aluminum in 3 moles of aluminum. Now here's where it starts to get a little complicated, so you may have to focus a bit more. What if, well, let me back up. What have we talked about so far? We've talked about converting between moles of something to atoms, or from atoms back to moles. And we used the Avogadro's number, 6.02 times 10 to the 23rd atoms or particles in 1 mole, right? That was our conversion factor. And then just now, we learned how to go back and forth between moles of a substance and the grams of that substance by using the molar mass of the substance as a conversion factor. So in these type of flowcharts, the arrows are going to represent an actual mathematical calculation using a conversion factor. Now, what if there were a problem that gave you grams of something, like I measured out 10 grams of some substance in the lab, and you needed to know how many atoms that was? We haven't learned that yet. We know how, if we have moles, we know how to get to atoms. If we have moles, we know how to get to grams. But what if you want to go grams to atoms? This may be the most important slide on the entire PowerPoint, all right? If you need to go from grams to particles, now remember, what is a particle? Anything that you can count. So it could be an atom, a molecule, formula unit, an ion. Okay, so anything that you can count out would be a particle. You cannot, in a one-step calculation, go directly from grams to particles or particles to grams. You cannot do it. Every conversion involving quantities of a chemical must go through moles, okay? Moles is in the middle of every calculation. So I'm going to show you that. I'm going to do a practice, but that's really, really important to remember this slide. Here is what we call a mole map, which kind of gives you the steps to do. I want you to take just a minute and figure out how to use this. We're going to ignore this whole leg of the map for now. We'll get back to that later. But I want you to see how moles is in the middle and that calculations have to go through it. So remember, there is no direct one-step path between grams and particles, okay? So for example, let's say if I started with, I say, okay, I have 5 times 10 to the 20th atoms, that's a particle, right, of carbon. How many grams is that? Okay, so you would look at the mole map. You'd say, okay, atoms, that's here particle. And I want to know how many grams. Okay, I know I can't do that all in one step. So your first step is follow the arrows. Your first step is going to be to convert from particles to moles. Everything has to go through moles. And in a second calculation then, you will convert from moles to grams. This is important to practice, a bunch of practice problems, okay? And this map is here for reference if you want to print it out or something. Here's an example. You have 35.4 grams of copper. How many atoms is that? So again, remember, if the word mole doesn't show up in the question, that means that's going to be the first conversion you have to do. So the process is the same though, dimensional analysis. Start with the given information, which is 35.4 grams of copper. Put the units you're trying to get rid of in the denominator of your first conversion factor. So now the grams of copper cancels out. Everything has to go through moles. Again, if the word mole doesn't show up in the question, that's the first step you're going to do in your calculation. Look on the periodic table. 63.5 is the molar mass of copper. Okay? And moles, again, goes on the top. And so if we did this in a separate step, how would we do that math? Well, so far we have 35.4 times, there's a 1 on top and a 63.5 on the bottom, right? So if you simplified it, what would it be in your calculator? It would be 35.4 divided by 63.5, okay? And that would give you how many moles of copper you have. So you can do it in separate steps, or you can do it as one long run-on calculation, which I did here. So let me walk you through the one long calculation. All right, so you set up the first unit cancellation. You got rid of the grams, and now if you were to stop, now you have moles. But the problem isn't asking for moles, it's asking for atoms. So I have to do another conversion, okay, where my units would be moles to start with, and I'm trying to get to atoms. So again, units must match on the diagonal so that they cancel. Now we're trying to get rid of moles. So moles has to be in the bottom. The units we're trying to get to need to be on top, in this case atoms. So you can do it as one long run-on. Okay, so where you would get 35.4 divided by 63.5 and then times 6.02 times 10 to the 23rd. And when you punch all that into your calculator, you get that 35.4 grams of copper equals 3.36 times 10 to the 23rd atoms. See if you can do this one on your own. So turn off the video and try to work it yourself, and then come back. All right, so we started with 1.20 times 10 to the 24th molecules of glucose. I'm going to put the glucose formula up here. There. And I'm going to remember, I'm going from molecules to grams. The problem asks for grams. And I know that if the question doesn't mention moles, that's going to be the first conversion I do. So I'm going to follow my rules of dimensional analysis. So I know that molecules goes on the bottom so that it cancels. And moles is what I'm trying to get to in the first step. And then put a number 1 in front of mole. What goes in front of molecule? Well, anytime you're doing a conversion involving a particle, remember atoms, molecules, formula units, you use Avogadro's number, 6.02 times 10 to the 23rd. All right, so now the original units and the units in my denominator cancel. And I'm going to go ahead and do this calculation in 2 separate steps just to show you that option. So if I do this math first, in other words, 1.2 times 10 to the minus 24 divided by 6.02 times 10 to the 23rd, I get, I'm just going to carry a bunch of extra digits for now until the end. Okay, and my units at this point are moles. because I'm going to look back at the question. The question's asking me for grams, so I know I need to do another conversion. So now the answer to the first conversion is going to be my given information, or my starting information for the second calculation. So now since I have moles in the in the numerator, I need moles in the denominator of my conversion factor, and I'm going to put a 1 in front of it. And what I'm trying to get to are grams. So I want you to get in the habit of anytime you see grams, that's when you pull out your periodic table. And you need the molar mass. And what are we talking about? We're talking about glucose. So the molar mass for glucose. So the molar mass of glucose is 180.156. You want to be careful at this stage in chemistry not to round molar masses to whole numbers, okay? We know the precision of these. So go ahead and write down all the digits from the periodic table. Don't round. All right, so now our moles cancel, and the math is simply 1.993 times 180.156, and let me go ahead and put that in my calculator. And so the final answer is 359, and the units, whatever the units in the numerator of your conversion factor, grams. So we're going to have to start worrying about sig figs, not worrying, but trying to keep the same number of sig figs. And usually that's the number of sig figs you had in the very original information. So that's 3 sig figs, right? And so as long as you're careful in all your conversion factors to have at least 3 sig figs, right, then your answer should have about the same number. Okay, so we're good there. So that is a sample of a 2-step process to get from molecules or any type of particle to grams, or the other way. You could also do it in one long continuous step, which I will show you very quickly. So instead of stopping and solving the intermediate mole, you would just keep it going. All right, and then at the end, you would just do all your multiplication, okay? Either way is perfectly acceptable. So that is an introduction to moles. So now we're going to get into chemical reactions and how do we apply moles to stoichiometry.